Guys, good morning. Welcome to our video series of modeling and simulation, system modeling and simulation. We are going to start going through the notes of the module. So we are going to use the notes I developed for the African Virtual University. So we are going to use the same notes. So this has been given to you. So this is a real book. It's a real book. So we are going to skip all these, I'm going to skip all these. You skip all these. Welcome to modeling and simulation. I don't know if you guys see. Yeah, let me increase the. Welcome to modeling and simulation. This module examines three-model computer modeling and simulation methods, namely agent-based modeling, system dynamics modeling, and discrete event modeling, utilized to simulate complex systems in health, business, science, and industry environment. The content has been taught to provide students with the trust of theoretical background needed to later practically develop, verify, and validate computer simulation model using the software AnyLogic 7. That is one of the rare simulation software tools that support three simulation modeling methods: system dynamics, discrete event, and agent-based modeling, and allows you to create multi-method models. So let's continue. So what are the prerequisites here? You are recommended to know detail of statistics, detail of probability, linear algebra, differential equation and integral calculus, data structure and algorithm, and object-oriented analysis, design, and programming. So you guys, you have all these background. So the core material will be, our AnyLogic 7 in 3 days, a quick course in simulation modeling. So this is a book I have shared with you, but there are also very useful content that you can read all there. The course goal. The goal of this module is to equip students with practical knowledge that will enable them to develop real-world simulation model from the start to the end. The software used is a modern one that supports different approaches of modeling and simulation, enabling students to acquire a working knowledge regarding the art of system simulation, characterize a system in terms of its essential components that are its purpose, stakeholders, constraint, performance, requirement, subsystems, interconnection, and environmental context. Gain hands-on experience on simulation software. Develop skills to use simulation software to construct and execute goal-driven system model. gain the ability to interpret the model and apply the result to resolve critical issues in a real-world environment. So we are going to have a different unit. The first unit is the first one. We are going to start from here. This one is not very useful, I'm going to start from here. In unit 1, we are going to introduce modeling and simulation. This unit provides the student with a broad understanding of modeling and simulation. It explores the different type of model and application used in simulation and details the steps of the simulation model lifecycle. The laboratory of this session will consist of installing any logic. And then we are going to cover agent-based modeling. In this unit, we are going to study computational models that simulate the action and interaction of autonomous agents such as people, organizations, or groups, with a view to assessing their effect on the system as a whole. In our laboratory, we will build an agent-based model of a consumer market, one where each consumer will be an agent, to help us understand how a product enters the market. For example, those doing business, those in business, this is a very good example, applied to business. In the unit 3, we are going to cover system dynamics modeling. This unit examines a perspective and set of conceptual tools that enable the modeler to understand the nonlinear behavior of complex systems over time using stocks, flows, internal feedback loops, and time delays, and use them to design more effective policies and organization. In our laboratory, we will build a model that simulates the spread of a contagious disease among a large population. Our sample model will have a population of 10,000 people. And then our last module will be, our last unit will be discrete event modeling. In this unit, we are going to study the process of codifying the behavior of complex systems with highly, stochastic variable parameters and constrained resources in order to improve the organization of delivered services. The laboratory of this session will create a discrete event model that will simulate a small job shop's manufacturing and shipping process. So those also doing business this is a very good example. Okay, this assessment does not concern you, but it's just like yours also, the continuous assignment will be 30%, the laboratory 30%, and the final exam. So it's almost like yours. Good. Now guys, let's introduce assessment does not concern us, So in the assessment here, we want to test whether you have the prerequisite, So I know you guys have the prerequisites, so we jump straight to introduction to modeling and simulation. Unit introduction. Simulation modeling has been used in a wide range of physical, social sciences, and engineering fields, ranging from nuclear fusion to economic forecast to space shuttle design. For different type of situation and system, different type of model are used. In classifying simulation, there are important distinctions among the types of model that are being simulated and among the type of program structures that are used to carry out the simulation. Objectives. So upon completion of this unit, you should be able to understand what is modeling and simulation, understand why it is important to simulate, differentiate the types of models such used in simulation, know different application of modeling and simulation, know how to develop, verify, and validate computational models of simulation. So let us define key terms. A model, what is a model? A model is a representation of something, an example for imitation or emulation. A description of observed behavior simplified by ignoring certain details. Models allow complex systems to be understood and their behavior predicted within the scope of the model, but may give incorrect description and prediction for situations outside the realm of their intended use. So what you should understand is that the model is a simplified representation of the reality. You see, like see in the construction domain, the construction before you build a house, you have to design the plan. So the plan of the house is a model. So it simplifies, the reality, because the reality is the house. It simplifies the understanding of the reality. So a model is something subjective. It is not objective. So it is why sometimes it can give incorrect description and prediction for situation outside the realm of their intended use. Even us, like in software engineering, you use different models, different diagrams, like the entity relationship diagram, like the use case diagram, the class diagram, and so on. So all these diagrams, enable you to understand, the reality, the environment, enable you to understand the system before you physically construct it in the machine. Now, what is a simulation? What is a simulation? So let's try to have a definition of simulation. Simulation is the imitative representation of the functioning of one system or process by means of the functioning of another. The imitation of the operation of a real-world process or system over time. The act of simulating something first requires that a model be developed. These models represent the key characteristics of or behavior of the selected physical or abstract system or process. So a simulation is what, just as I told you in the introduction, in the welcome, and also in the welcoming video, a simulation is an imitation. You imitate, a process, because you don't have the means of doing that in the reality, because it will take time and it is very costly. So then you can simulate it in a logical world, in a virtual world, and have your output just like we have seen in the statistics. Now, what is modeling? Modeling is a way we can solve real world problems. In many cases, we can't afford to experiment with real objects to find the right solution. Building, destroying, and making change may be too expensive, dangerous, or just impossible. If that's the case, we can build a model that uses a modeling language to represent the real system. The process assumes abstraction, We include the details we believe are important and leave aside those we think are not important. The model is always less complex than the original system. You see, the model of a house, for example, is less complex than the house itself. By looking, if for example, look at the house where you are staying. If to tell you to to understand it the way it is, in the real world, if they tell you to draw something similar, for example, it will be very difficult. But with the plan of that same house, you can easily understand, you know, uh, the structure of the house. For example, you see that this wall is measuring like 3 meters or 10 meters. This window is measuring like 2 meters or 1 meter of width or height, and so on. So modeling, simplifies the process, and it is also expensive. Building it is sometimes dangerous. Building the model, and it's just sometimes impossible to do that. So in the real world, in the reality, so you model it then, and then you simulate. When you simulate, you have the output, in the statistics, just like we have seen. So it's going to tell you, if it is a clinic, for example, it's going to tell you, uh, for example, how many nurses you want, how many medical doctors you want, how many patients you are likely to proceed per day. So this will give you useful information and decide accordingly if it is worth, opening a clinic. Now you guys see the difference between the model and the reality. So down we have the real world, made of physical houses, and then the model is what is up here, the world of model. See, world of model versus the real world. So what is up, what is up here are the models, the world of models, and down is the reality. So this one, simplifies. So it just gives, the detail you want to know. It does not move into in detail. So it is why models sometimes or most of the time are more useful than. Now let's talk about useful concept here. What is an entity? An entity is an object of interest in the system. An object of interest in the system. Just like entity in database, we have entity relationship diagram. An entity can be student, can be a bill, can be an invoice, it can be a room, can be anything, with interest to the system. And an entity has attribute. An attribute is what is a property of an entity. An entity. For a student, we have attributes like the registration number, the name, the the date of birth, the gender, the photo. So these are attributes which characterize a student. Now, what about an activity? An activity is a predefined set of action in a specified time period. So an activity is made of action, which are systematically organized, and they are predefined actions, which are systematically organized and which happen in a specified period of time. Now, what about the state of the system? The state of the system is a collection of variables that describe the system at any time. So what is the current state of a system? What is a state? A state is, a state describes the situation of an entity at specific time, or the characteristic of a system at specific of an entity at specific time. Now, or it can be the characteristic of the whole system. For example, a state of the entity student can be applicant, your applicant, and then your admitted student. That's another state, and then you become a registered student, and then you become a graduate student. So we move from one state to another. So the state of the system, can also be, for example, the system is dormant, for example, or a system is working, or a system, is off, has stopped working, stuff like that. So this is what we call a state of a system. What is an event? An event is an instantaneous occurrence that may be associated with change of the system state. An event, like in programming, we have different events, like a click, when you click a button, for example, or when you place your mouse on top, of a button, or when you load a page. These are, things happening. These are occurrences that happening, and this is associated to the change in the system. For example, an event like clicking on the button save is triggered by the fact that in the system there is a new student who wants to be recorded in the database. So then you are going to enter the information of the student, and you are going to click on the button to save the detail of the student in the database. So this is, an example of event. Other example of event, in the real world can be like the lecturer arriving, a client, arriving, a client leaving, a client paying, a client carrying his goods, a truck, delivering product, or an agent, a delivery agent delivering food. So these are examples of event, and there are many events occurring in the system, and these occurrences are conditioned by the state of the system. System environment: region outside the system that influence the system behavior. A system is a closed entity, just like you see in use case diagramming. In use case diagramming, you see the use case diagram depicts it very well. You have system internals, and outside the internal of the system, you have the actors. If you don't belong to the system, you belong to the environment of the system. But this environment highly influences the system. For example, if you have an accounting system, and you are recording information, retrieving information in the system, you, the user, you are the one instructing the system to do what you want, but you belong to the environment. You see? Now, another example is if we were in a physical class, or even if it is an online class, it's still a system, because if you don't attend system modeling and simulation, you are outside our system. You get that? So but we are influenced, for example, by the university's administration, which sets the rules, which is going to say, okay, now you guys can study online, you can start this time, you end this time, as per the timetable, and you can uh, uh, you cannot exceed this time. You have to take your exam this time. You have to submit marks this time. So the university administration is outside our our system. Our system is closed. It's made of I, the lecturer, and you guys. The student taking system modeling and simulation, and uh, our interaction. So of if you are not part of our system, you belong to the environment. But this influence, the environment influences the system. Now, why simulate? Why simulate? Why should we simulate? It may be too difficult, hazardous, or expensive to observe real operational system. Part of the system may not be observable. For example, the internal of a cyclical chip or biological system. Analyze systems before they are built. Reduce the number of design mistakes. Optimize design. Analyze operational system. Create virtual environment for training and entertainment. You see, why do we simulate? It can be very expensive, to build, for example, a plant, or to build an industry or a clinic, go rent and then start before you try to understand the internal of the system. So it can be difficult, can be hazardous doing that, or sometimes some element may not be observable, like biological system, like the digestive systems, in our body, or the nervous system. Some part may not be observable. So simulating might be useful, analyzing system before they are built to try to understand them, before we decide, building. Reduce mistakes, optimize the system design, and analyze operational system. Also creating a virtual environment for training. Take for example training pilots. It can be super risky, to engage a student, who is learning how to pilot in a real plane. It's totally crazy and very dangerous doing that. So what you do then, you build simulators. These guys are trained on simulators. Even guys in the army, they are trained in simulators, before they move into real systems. When is it appropriate to simulate? Allows access to system internals that may otherwise not be observable. Informational, organizational, and environmental changes can be simulated, and the effect of these changes on the model's behavior can be observed. Observation based on simulation give great insight into the system behavior, and it can be determined which variables are most important and how they interact. Analytic solution can be verified. Simulation allows to experiment with new design or policies prior implementation. So basically, it is important to simulate, when system are complex, they are not easily observable, you know, and or part of the system, even if it's not the system, the entire system, but part of the system may not be observable. You know, it is important to simulate, when there are huge interaction, between the component of the system. It's important to simulate, when I mean when it's possible, to verify, the solution, to analyze the solution and you verify them. It is important to simulate, when you are trying different alternatives, when it comes to design a new system you would like to operationalize later before the system. So it can also be used for training without the cost of decision of on-the-job learning. Like I've taken the example of guys, being trained to pilot, this engine, this machine costs, hundred of thousands, so you cannot take that risk, and their life is also at risk. So the simulation system is too complex, that is interaction can be treated only through simulation. So that is, when it's important to simulate, when it's not appropriate to simulate, when common sense surfaces, so why simulating? Why wasting our time engaging simulation engineers building models, simulating them, when the system is obvious? Sometimes there might also be no analytical solution. When it is easier to perform direct measurement on physical system. When there's a shortage of resources for implementing the solution. When the feasibility is not possible. When there's a shortage of time for getting the desired result. When data is lacking for modeling the system and beginning a simulation study. When there is enough time and personnel to verify and validate the model. When managers' expectations are unrealistic, when the system is too complex to be modeled. So in this situation, really is not appropriate to simulate. Now, you guys, what are the areas of application of simulation? I hope the resolution allows you to see. You can see that you can apply simulation in a quite wide range of areas. From, if you try to read a few from the bottom to the top, in control system, in computer hardware, in battlefield, in traffic, manufacturing, in rail yard, in warehousing, in hospitals, in call centers, in business processes, in supply chain, in fleet management, in project management, in human resources, in market and competition, in economics, in ecosystem, in social systems. So you see, you can apply, almost in all the apply simulation almost all the areas. Now you can see that they are clustered into three levels of abstraction. We have the low abstraction level, we have the medium abstraction level, and then we have the high abstraction level. So it means what? It means that these areas down here, like battlefield, traffic, pedestrian movement, computer hardware, and control system, have a low abstraction. It means they are less complex to simulate. They are not complex to simulate, but This in the middle here, supply chain, transportation, call center, business processes, hospital, warehouses, airports, they have medium level abstraction. So it is not that uh, difficult, but it's not also that easy. So it is 50-50. They are not too complex, but they are 50-50. They are considerably complex. Now, those on high abstraction, these are social system, ecosystem, economics, market and competition, project management, human resource. These are very, complex system to simulate. So they are very complex for a reason, because when it comes to understanding social behaviors, it is very difficult. When it comes to understand the economics, the market, the competition, these are very dynamic systems, because they are made of um, you know um, social systems which are very difficult. They are made of uh, non-linear systems, like human being. The most complex system you cannot understand are human being, like social systems. How human behave, you cannot predict that. So because humans are, non-living system, they are living system, and their interaction, their dynamics, are very complex to understand. You see, like human resource is very complex. Market, you know, uh, how the market, fluctuate, in terms of the offer, the demand, the importation, exportation, the macroeconomics, even including the politics, the demographics, and so on. This is huge, huge stuff to understand. So the complexity here is very high. So is why the level of abstraction is high. So these are the areas of application. Good. Now, application in critical decision making. Now, application in critical decision making is what do we mean here? Is when simulation is risky. For example, it is engaging human life. When it's engaging human life, for example, here uh, we have simulating. Here you see an aircraft. You know, uh, 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 it's very risky. It's very dangerous. If you simulate, um, if you want to physically, simulate in a real plane, you know, if you don't have enough training, this will lead to a disaster. So simulation helps then to to mitigate this risk. You know, so you can simulate, an aircraft, you know, an aircraft with a system. You see a simulation system. So here we have analysts and decision makers, who interact with the simulation system, and they read the output. So modeling and simulation can be very important in risky situation, like training, pilots, like earthquake, so like battlefield, you know, instead of engaging uh, real real soldiers in a battle to try to simulate a battle. So it can be very useful to simulate a battle, for example, air traffic control, battle management. So these are very risky situation. You know, simulation tools is used for fast analysis, of alternate courses of action in time critical solution, analyze simulation from situation database faster than real-time execution to evaluate the effect of decision. For example, in a battlefield, you know, simulating with real soldiers can be very expensive. It can also be risky. Though you are not using real bullets, it can also be risky somehow. It's also expensive, it's taking time. So you can then simulate a battle before you do it physically. You can simulate a traffic control, air traffic control, you know. So I think we have examples here. We have training, for example, military, pilot, medicine. Yeah, medicine is very important. Actually, we have simulation tools, which enable a student in medicine to simulate an operation, for example. Doing it in real human being can be super risky, and even on animals, sometimes this guy defending the environment, they make noise or whatever. So to avoid all these, you can use simulation. In defense, for example, automated forces, semi-automated forces, physical phenomena like earthquake, you cannot engage you cannot engage an area like a district or a city in a real earthquake, simulation. That will be super crazy. So, but you can simulate the damage of an earthquake, on the population. For example, if an earthquake happens in the volcano areas there, what will be the damage, so that one you can simulate it. But it will be super crazy, trying to do that physical trajectory projectile, even buildings, construction. When you, for example, you want to analyze the strength, and you want to analyze the strength of material, if material are going, like a bridge is going to is going to support, a given load. You see, like you want to try if a bridge is going to may resist to a super heavy truck, for example. You can simulate that for how long and so on. You see, so it will be super crazy trying to do that in a real environment. That's it. So in the next video, we are going to talk about type of simulation and try to understand them. So you guys, I wish this video has been helpful. So I would like to thank you guys for watching. So see you in the next video. Bye bye.